one more video. I'm going to show you the specific results for the logistic model. I'm a little annoyed because I just recorded an entire video in which I forgot to share my screen. Getting a little punchy. And I also, just because I watched the previous one, I want to just lay to rest any ambiguity as to what my t-shirt says. My t-shirt says vaccines cause adults, because they do. Because you vaccinate your children against children's vaccine preventable diseases, and they survive to be adults. Having laid that to rest, I am now going to share my screen. Important feature of doing a whiteboard session. And I want to just remind us about we've got f of n equals Rn for the logistic model, 1 minus n over k. Okay, and so, oh, good Lord, I don't know if you can see that. To find the equilibria, we set that equal to 0. It is a product of two things, right? It's a product of R times n, and it's a product of 1 minus n over k. Right? Those are the two things that we're multiplying together. That means that we have two conditions under which the left-hand side of the equation here can be equal to 0, right? And that's when n is equal to 0 from this first condition, and when n is equal to k in the second condition, right? Because 1 minus k over k is 1 minus 1 is equal to 0, and r times 0 is 0. Okay, so those are the equilibria, just to recap. Now, you may remember that for our linear stability analysis, we want to look at what happens to a small perturbation, right? We call it little n, with respect to time. And we showed that it was equal to f prime of n hat. So the derivative of the function of this, right, at the equilibrium values. And for simplicity, because it's easier to say lambda than it is to say f prime of n hat, right? Oh, and there's an n in there, is equal to lambda n, okay? And that comes from, the Taylor series, because when in doubt, Taylor series it out. And if lambda is greater than 0, then the perturbations grow. If lambda is less than 0, then the perturbations decay back to the equilibrium, and you have a stable equilibrium. All right, so we showed sort of qualitatively, intuitively, using a graphical approach, how you can sort of reason out what these equilibria are, whether they're stable or not. But now we're going to show it more formally, and so we need to calculate f prime of n hat, right? So that means we have to calculate a derivative of f of n. So the derivative of f of n, as we've already said, is a product. It's a product of two things, and that means that we have to use the product rule from high school calculus or first year calculus. And we may remember that when we have some function h of n that is a product of two things, f of n and g of n, okay? H prime of n, what's it equal to? It's equal to f prime of n times g of n plus g prime of n times f of n. Okay, and our f of n is the first thing in our big f of n, the first multiplier. So is Rn, and g of n is equal to 1 minus n over k. The derivatives of those, f prime of n is just equal to r, right? The derivative of Rn with respect to n is just equal to r. And the derivative of 1 minus n over k, g prime of n, is just equal to minus 1 over k. All right. So we can now do our substitution. So f prime of n is equal to, the capital F prime of n is equal to f prime of n times, is that right? F prime of n, yep, times, should be confident, n over k, plus g prime of n, so that's a minus 1k, don't screw up your signs, as I often do, times f of n, which is r times n. Now, that's generically capital F prime of n, but what we want is f prime of n at the equilibria, right? F prime of n of n hat. So let's look at our two equilibria. So for n hat equals 0, we just substitute n hat in for wherever there's n in our equation. So we have r times 1 minus 0 over k, 0 over k, right, plus minus 1 over k times r times 0, and that's equal to, right, that's r times 1, and r times 0, it's just equal to r. All right, so the derivative of our logistic function at the equilibrium for n hat equals 0 is just equal to r. Now let's look at our second equilibrium, n hat equals k. So we have r times 1 minus k over k. That's equal to 0, plus minus 1 over k times r times k. All right, so that's equal to 0. Those two cancel out, and what we get is minus r. What does this tell us? When we are at the 0 population equilibrium, right? It's an equilibrium. The population won't grow there, but if we perturb it, and we can only perturb it up, right? Because we're at 0, we can't have negative population. It doesn't make any sense. If we perturb that at all, that population is going to grow. That perturbation is going to grow at a rate r, which is, right, the exponential rate of increase of the population, right? So initially, the logistic growth grows at approximately an exponential rate. Okay, so that's good. The second equilibrium, n hat equals k. If we perturb it, right, what's going to happen? It's going to decay back down to that equilibrium at a rate minus r. And so the negative equilibrium, or the negative slope on the perturbations, the negative growth rate on those perturbations, means that this equilibrium is stable. All right, so this one's stable, and this one is unstable. All right, and just to remind you of when we drew this graphically, intuitively, we plotted n. This is called the recruitment curve. The change in n as a function of n, and it looks like this. It's humped. It actually can get negative at the upper end. It can't get negative at the lower end, because that would mean that you'd have negative population. We have these two equilibria of n equals 0, n equals k. Okay, and if we perturb at the 0 equilibrium, if we perturb it up to here, then what do we see? Well, we can look at the graph. What does the graph tell us? Right, it tells us that it's going to increase at whatever that value is, right? So it's greater than 0. Probably shouldn't have made these dotted lines, because it means I have to undo all those. That's okay. And so that means that it's going to grow away from that. right? And that's exactly what we see in our first solution to the linear stability analysis, right? And then if we're say here, if we're shy of the carrying capacity, well, of course, the population is still growing, right? So it's going to continue to move up towards K. We knew that already from the recruitment curve. If we're out here, right, so we can draw an arrow there. If we're out here, well, that means that we're actually going to decline. The change in population size is going to be negative, right? Because the death rate is going to exceed the birth rate, and we are going to, and we could draw it down to there, wherever that extension is. It's going to be over here somewhere. It's going to be negative, and that means that the perturbation will decay back there. And graphically, when we have a stable equilibrium, we're going to have this sort of situation, right, where the arrows point in both directions back towards the equilibrium. So that's our stable equilibrium. This one is unstable because there's only one arrow and it's pointing away from the equilibrium. If it pointed back down, then it would be stable. But it's not, it's pointing away. And that makes sense. You can't grow when there's exactly no one in the population, but as soon as you start adding people, right, you can grow. And similarly, right, as soon as you exceed the capacity for the like the ecological, the carrying capacity of the population, you're going to have deaths exceed births, and you're going to have the population come back down to the equilibrium. So I hope that's useful to see this graphical approach, to see this analytical approach. It's very unusual to have the rate of return or moving away from the equilibrium be just like opposite values of the same number. It has to do with the peculiarities of the logistic model because it's a linear model, and it's very symmetrical. If we look at the recruitment curve, it's perfectly symmetrical, right? The maximum sustainable yield is K over 2. In general, that isn't the case. In general, that you're going to have different slopes at different points in your functions when you do linear stability analysis. But I hope this has been useful, and I hope it helps to build the thing that I really care about is building intuition, because this is how we start to understand things like forcing and what forcing can do, catastrophes. What does it mean to be a catastrophe? This is how we think about, right, stability, right? And this is how we think about resilience. These are really important issues in adaptation and thinking about global change and ecological change. And they all turn basically on linear stability analysis. And so we have to build up our intuitions about linear stability analysis in order to really understand what's going on with these important ideas. So I hope you find this useful, and we will see each other virtually in class on Tuesday.